Now I'd like to introduce Karl Andersson, a research officer in soil carbon from New South Wales DPIRD. Karl is a soil scientist with 25 years experience throughout New South Wales. He's worked in regions from the high rainfall to the semi-arid zones in fields including soil mapping, agronomy, soil carbon, nutrient cycling and irrigation, dryland and urban development. Based at the Tamworth Agricultural Institute, Karl works to enhance soil management practices within the New South Wales agricultural sector and is an experienced researcher and communicator of soil carbon information.
All right, thanks, mate. And hello to everybody. So what I wanted to talk about today was not soil carbon in the rangelands so much, it's just a little change, soil and carbon in the rangelands. A lot of attention on soil organic carbon, which I think falls down to carbon as the focus, and sometimes people then talk about organic carbon, but it's the soil that I want to focus on being the most important thing. And really what the discussion is about organic matter, carbon as part of the organic matter. So that as an intro, the topics I'm going to run through is just looking at some soil types through the rangelands, having a bit of a discussion about carbon cycles and levels, and then getting back to the organic matter and management of soils. So the setting of where we are talking about for New South Wales rangelands is west of the white line there. That's the sort of formal definition of rangelands. So basically we're talking about low rainfall soils environment, sort of pushing up towards 400, 450-ish mils. So with low rainfall, the properties of the soil become so much more important. A bit of a background for some soil types, some soil properties now. This is extending out of the rangelands, but just for contrast, the three profiles here are from a granite. It's the same granite material in each of these places. Up in the high rainfall area, up around Tumbarumba in the snowies, is the one on the right, in the middle here on the right-hand side. We've got a really high organic surface, that dark material there accumulates. And as we go down the profile, there's a zone of depletion and leaching before we hit into the clays. Coming a bit further west towards Wagga, we've got the same material again, but less of an accumulation in the surface. It's got a pale layer, but it's less distinct, and then we're getting into the clays again. But now coming out to Mount Hope, north of Hay, the soil, we don't have that rich sort of accumulation of organic matter in the surface, and we don't have that vertical sorting either, that sort of zone of depletion. So in lower rainfall areas, we're dealing with less organic matter in general. We also have changing soil properties on slopes. Closer to the top of the hills, they're generally shallower. Moving down, we've got deeper soils, but also some chance for this accumulation of organic matter. Large parts of the rangelands are occupied by alluvial systems of different ages. There's current rivers, but there's lots of older rivers that have given us the sediments and the soils that we've got now. On a simple view, as a river flows down, the coarse sediments get dropped in the channel, the sands and gravels. As it floods, the finer sediments get lifted up and over, the fine sands start to fall out. And as we get out into the backplain areas, that's where you get your heavier clays. And these photos here show the changes you get moving away from the channel. Now, we've got our current channels, but a lot of these areas are older channels. And we can see an example here where an old channel is moving through this meander plain and the quite distinct changes in soil types within a fairly short distance. The relevance of these older systems is that the older they are, they're now abandoned, they don't flood, so they can accumulate salts, which sit in the profile. Another key influence out in the rangelands is windblown dust, often coming out of these dry lake beds, which blankets the landscape, and large parts of Southeast Australia. They can often also be salty as well. We can see those on the ground with different shaped dune systems. And then down in the southwest of New South Wales particularly, we can get some of these soils where, if you think back to the other ones, we've got sort of reddish material on top, but this white material down here is full of carbonate, so inorganic carbon as opposed to organic carbon. Sometimes a relic of marine incursion into that part of the landscape up to, say, 5 million years ago. So lots of differences in our soil types that influence how they operate and the accumulation and cycling of organic matter and carbon. On to carbon. What is it? As I've touched on, it's part of organic matter. We just measure carbon because it's the easy part to measure out of the organic matter. It's typically dark, as we saw in that profile there. Carbon is important as the skeleton for other components of organic matter, and basically bugs see it as a source of nutrients and energy. So it goes cycling, and it's a really important thing for your soil. It supports all the productivity and resilience in it. The carbon as part of it is around 57%, depending, and it varies quite a lot, higher proportion in fresher materials. And it decomposes through into different forms of different stability, which also do different jobs in the soil, of holding the soil together or keeping particles from collapsing too close together and setting hard. If you're looking at measuring carbon for knowing how much there is, say for carbon trading type schemes, then a key part of what you need to know is not just the percent of carbon, but the bulk density, which is the amount of soil in a given volume. Bulk density changes much less so than does the carbon level, but a way to sort of represent that bulk density is that a bulk density of 1 represents, through 10 centimetres, 1,000 tonnes per hectare. And that becomes important when you're looking at changes through time, that you're measuring the same amount of soil, not just at given depth. So that then gives us our carbon stock. The percent times the bulk density gives us how much carbon there actually is in that area. So as opposed to looking at carbon as a sort of currency of soil health, which is where I'd like to focus more, that calculating for stock and understanding how much of that there is needs this bulk density and those sort of accurate measures there. So moving to how it moves through the landscape. Even just this background photo is useful for looking at soil properties here. This was on an area that had previously been scald and was self-ameliorating over time with some careful management. And the patchiness is really important, and the types of vegetation on there. So we've got these sort of copper burrs and salt bushes that are fairly tolerant and hardy, and then the grasses and the forbs accumulate around those. Where those plants are, the soil is in much better condition than the bare patches. So you can walk through here, and the soil in the bare patches had a salinity of somewhere like half seawater concentration, around 30 decisiemens, which is really, really hard for plants to put up with, let alone establish in. Under the plants, that top 20 odd centimetres was much fresher. The plants are protecting the soil from raindrop impact, minimising evaporation from the surface, which accumulates salts at the surface. So you start to get that positive feedback by having plants in there. So the soil organic matter, which is the breakdown of the plant material, we think of it, we sort of divide it into these pools, roughly into the particulate form, the fresh, coarse material that is readily decomposed, cycled by soil organisms. The mineral associated is where it's broken down into its more basic components, and it's got charges that can then stick to the clays, say, or active parts of the soil. And then there's a more recalcitrant, stable type of form, which is sort of generally charcoal material, labile, easily decomposed, and there's different levels of protection, be it physical or chemical, in the soil. Of course, it comes in through photosynthesis, through those plants to start with, through litters of manures and the biomass of roots and exudates. We get all that sort of combines through the organisms into the soil organic matter. As they're doing that, they're respiring the bulk of it, and any disturbance in the system can increase that rate of respiration, be it physical disturbance of turning over, or even just changes in the amount of rainfall or temperature changes can change the flux rates. There's product removal out of the system, and also erosion is a key component, and hopefully not too much, but it does occur and get run off through these bare patches, and even more so in the rangelands. Wind erosion is a key process, so much so that some work has shown that the organic matter in the dust that's blown off can be 8 times the concentration of the organic matter that's actually in the surface. Being so light, it can be lost fairly readily. So again, that presence of plants is really important. So what do our stocks look like? Stocks, remember, it's the percent of carbon and the bulk density. So through New South Wales, there's a clear pattern there of low stocks in the west, in the rangelands, to higher as you're moving into the higher rainfall areas. And the different patterns there, we're starting to look at the different soil properties like the parent material and the rainfall and the alluvial systems that I referred to earlier. That explains these different shadings through here. So that's where we're sort of generally where we're sitting. Of course, there's more subtle variations underneath that. But going from here, what could you look at in terms of increasing? The same paper with John Gray showed the potential increase modelled with an increase in long-term vegetation cover. And again, the potential levels for increase were relatively low in the rangelands, just because of the lower rainfall and also the erratic distribution of the rainfall. You get very dynamic systems in the rangelands, rainfall leads to plant growth, but the longer periods of dryness between that allows all organisms to cycle that through and to maintain those lower levels, which is not in itself a bad thing. If the soil is supporting plant growth and the material is cycling, that's actually the good thing. The fact that the carbon levels aren't necessarily going up is just representative of the cycling of the nutrients and energy through the system. So what do some numbers look like below that type of level? Here's some data from around 8,000 samples we collected a few years ago in southern New South Wales from the dry areas right up into the hills. And the sort of pattern there, real feature there, is that there's not much response through up to about 500 plus mils, fairly flat constant levels. It's above that where there's scope for increase in the surface and even higher rainfall required for increases in the lower layer. This green arrow shows the area that we're talking about in the rangelands, up to that sort of 450 mils. Vertically, deeper through the profile, what could we look at? Here's some samples that we collected part of the Rangeland Living Skin project recently finished from Pooncarie down on the Darling sort of area, southwestern New South Wales, and Cobar, the Cobar Penny Plain area in central western New South Wales. Cobar's got a higher rainfall, which is reflected in that surface accumulation here, trending upwards. As we're running down the profile, carbon is depleting. Out at Pooncarie, where it was much lower rainfall, we're sitting on lower levels to start with and fairly vertical type, not much of a difference as we're going down the profile. These different lines are, the landscape was broken up into different strata to try to represent the different soil types. What's quite interesting here is the green line, where we've got an increase in carbon concentration lower down. And if you think back to that profile I showed earlier with the white material in it, that's what's probably being represented there. The testing process intended to remove that, but it's not necessarily as complete as it could be. Sometimes the nature of those materials can be quite hard, so they can be fairly resistant even so. So that's probably what we're getting there. Amanda Chappelle's done a lot of work in South Australia, so over the border, a similar type of pattern of carbon levels with rainfall. Carbon levels on the vertical and rainfall on the X there. She's represented here with different textures. Similar pattern, different sort of scale with each one. The lighter material doesn't quite get as high, the sands, as do the clay loams and loams. The different lines in here are what they've picked up over a number of soil tests with low levels, average, and levels that you might hope to be able to get to if the soil is degraded, with a really high stretch target, as they call it. And the aim then, if you're looking at these lower levels, is what you could do to be able to increase up to those more achievable levels to help support production. So how can that actually be achieved, and what does it look like over time? This bit of work is from Condobolin, where Warwick Badgery and the other authors got the data from the Condo Research Station collected over a number of years on different farming systems. The codes here are different cropping treatments and a perennial pasture in there as well. The pattern we've got from over those 13 years there is increasing carbon levels in all the treatments, which is nice. And that's even reflected lower in the profile as well. A little bit longer, but then that sort of lag coming through. Bit of a kick up there in that perennial pasture. That's similar to the chart earlier on, process-wise. However, in the subsequent measurement in 2015, all of that material had disappeared, and even lower in the cropping treatments, and again in the subsoil as well. So the key thing is appreciating that with the cycling of organic matter, there's increases and decreases, but how we can operate with that and maintain those levels to help support the systems. If we just put that graph back onto the full axis from 0 up to 2% here, so what we're doing is sort of looking at that we're operating in this window, and so long as what we'd like to be doing is potentially increasing those levels, at least maintaining, but over time not seeing them fall away. Because as they fall away, we're losing that cycling that supports our ag systems and soil resilience. Unfortunately, that's as far as that data goes. Those practices were stopped at that point. But more recently, Abe Gibson at Southern Cross has been doing some farming systems research out there with different fallow management and summer cropping and species mixes. And what is found, again, reflecting that marginal rainfall, is with the low biomass, the soil microbes respond to any sort of input of organic matter. So overall, there hasn't been a real change in their carbon levels, which just sort of sits with this type of idea. More broadly through Australia, that was cropping, but what about grazing management? Grazing management is often seen as a potential way to increase soil carbon levels. Sarah McDonald and co-authors a couple of years ago did a review of what was available to help explain that or support that. And what they found was that from the available studies, relatively few really, but 30 studies available that looked at grazing and soil carbon, there was no significant impact of how stock were managed. That doesn't mean that there wasn't any influence of stock management. You could get increased biomass, ground cover, productive perennials, but again, that cycling of the organic matter coming through is a really good thing to see. So it's not a negative to say that your levels are just sort of staying flat. And again, I just want to reinforce that it's not just carbon, it's soil and soil organic matter. That's really important. So what can carbon organic matter provide or help in the soil? It can really soften up these soils that are collapsed and no structure and dispersive. The pale colour you can see, it hasn't got that dark layer on there. We've lost our surface. There's no sort of resilience to it. Hopefully this little video works. You can do a little test yourself on stability of a soil. And this is the key thing that organic matter provides in the soil. It provides a stability when the soil is wet. Resilience to raindrop impact is one, but also the ropes basically and the glues help hold the soil together. So that was the very surface, darker, and the subsurface there, the paler material. And this is real time, so just rapid slaking of this soil. If that's the surface, then we're ending up with this sort of material where it's just sealing off and rainfall just can't get in. So low rainfall environment and not being able to get water into the soil is a real problem. Some other constraints that may be relevant to processing in soils and cycling of organic matter. These numbers here are results of sampling that we did through the Rangelands over the last few years, where producers selected their own properties, own areas of their properties that were of interest, and we've measured the sodicity, the dispersiveness, and the salinity, the ECE. And carbon's up the side here. So the higher the sodicity is, the higher the dispersiveness, the lower the carbon levels tended to be. And similar for salinity. It's not a set rule. It doesn't mean that just because you have low salinity or low sodicity that you do have high carbon levels, but that was the sort of general pattern. So the less constraint to plant growth, the higher the level that you could be looking at. Sometimes these sites areas can be really degraded. Here on the left, we've got this soil that's just lost its surface. It's gone, but we've got banks constructed. So Paul Theakston's busy out Western LLS doing a lot of these banks, and it's really marvellous to see the effects. So from the air, you can see the effect from the ponding of the water, just slows it up, allows plants to grow, and chalk and cheese type of effect. That's one thing. Ponds or banks, livestock may also be successful in these sorts of areas, adding things like gypsum to help stabilise dispersive surfaces. Whatever the constraint is, an appropriate type of solution. Here's an example where we did do some gypsum on a really bared off scald, and you can see on the right hand side the response early on, and 12 months later the response is really sort of bedded in. It's not entire coverage. We've got more ground cover, more vegetation there, much more than the absent side. And what we're getting with that vegetation cover is more infiltration, so about 40 centimetres more moisture into that soil, which just will help keep supporting that system. The ponding, the gypsum application, what they do on these degraded sites is often there's a problem of salinity, and what they do by getting the water in is flush the salinity. So the black line here is the salinity of that site, of that scald there, when we first looked at it through the profile is about 45 decisiemens. 50 odd is seawater, so it's pretty high. With these solid lines here, so the year later there'd been some decent rainfall, so a little bit of the surface had actually flushed clean, so it will flush down, deeper down in the profile. It's still high though on those bare areas. Where some vegetation had grown, that then reinforced the system, and we're getting even more effective flushing of the salts. And then down below 10 and 5, that's been quite good. And then we're just sort of hoping to push those salts deeper and deeper to increase that root zone. I guess a way to look at the effectiveness of soils and a functioning landscape is this process called landscape function analysis. There's a bunch of indicators that you collect of the soil surface on a transect. Those measures then get used to indicate the soil stability, the infiltration of rainfall, and the nutrient cycling. And to use that sort of approach, look at the effect of ponding, where measures were taken in the control area outside, and then on the bank, and then stepping out from the bank, 2.5, 5, 10, 20 metres. So walking out from where the ponding was happening out beyond the effective ponding zone. And what that showed was that by slowing up the moisture, by slowing up the rainfall running off and kick-starting the system, there was more infiltration. So not just that the water sat there, but the water got in. It helped then support the growth, which also got the bugs active, and what was coming in was also being cycled. So again, we couldn't necessarily inspect beyond the very surface much of an increase in carbon because the bugs are cycling. So right at the very surface, 0 to 2 centimetres, there was an increase in organic matter, which is terrific. 0.4 is really low. 0.7, we'll still be looking for higher than that to give that stability. That surface is the throttle for the system. So once that gets more resilient, then we can support the system. Coming back to what you could do in terms of managing the soil carbon, soil organic matter, is maintaining what you have. So rather than even just thinking about increasing, maintaining what you've got. So not having losses in the system, not having areas where water can be running off or soil can be running off or blowing away, maintaining that as best as can. And definitely not revisiting these sorts of scenes where massive amounts of soil have been lost. The reason I just popped this one in here is just sort of to remember that some of the systems and soils out there are degraded historically, and trying to rebuild them isn't just the same as saying, okay, well, we lost a bit of organic matter from it, we'll just put it back in. The entire soil is different, often harder to repair and start going again. And again, just bringing the message back to soil organic matter. I thought I'd just touch quickly on carbon trading, where there be maybe some interest. The system is under review at the moment, and any sort of updates will be coming out shortly. I don't imagine that these sorts of things will change. These are the practices that are acknowledged as being additional to existing practices that could mean there's a change in management, which could be looking to increase carbon in their soils. All of them are basically agronomic activities. They all point to dealing with any sort of constraints or looking to improve agronomic outcomes in any case. To go down the avenue of a soil carbon project, questions that you'd be looking at is what sort of commitment is required? Changing practice, but how long do you need to change it for? Do you want to keep doing that? Does it work for your system? You want to take some preliminary measurements and understand where the soil is up to. You would want to be aware of statements such as where I've heard people make guarantees of increases, that there's infinite capacity of soil for carbon, that adding it is easy. Those are things that are said, but that's not necessarily the case at all. What evidence is there to support that there'd be an increase in levels on your place? Anything relevant to you, given the information that we've just been discussing? So by way of summary now, the key points is that rangelands are very dynamic and variable, and the key thing is to maintain organic matter, the soil surface and the ground cover. Really important. Addressing any constraints you've got, use observations and soil testing can be really useful. Building organic matter or carbon with growth, plant growth, while minimising outputs. Mineralisation is part of what happens, but minimising that erosion is really important. And what the evidence base is, and as I said, historic loss is common and recovery is possible, but it's not necessarily always straightforward. So yeah, maintaining that nutrition and productivity is what's really key for your situation.
Thanks, Karl. Fantastic summary and rebalancing of how to look at things.